Hi, this is Team 11. We did Maze Generation. We total a team of 5 members, and my name is Lincoln Alexander. I'm a junior here at UCF, studying computer science. I mostly managed the LaTeX document and made sure the quality was up to date and worked on the PowerPoint.
Hi, my name is Stephen Horn. I'm a senior here at UCF. I mainly worked on randomized prim and also the LaTeX document and PowerPoint.
My name is Shrignan Parachiru. I'm a junior at UCF. I worked at the randomized DFS code implementation. I worked on it both sequentially and concurrently. I worked with 2 threads, 4 threads, and 8 threads. And I also worked on the charts for the programs, the average maze time and the average runtime.
My name is Brendan Rubio. I'm a senior, and I worked on randomized prims algorithm and coded a sequential and concurrent implementation.
My name is Caden Lair. I worked on the Alias-Broger algorithm both sequentially and with 2 concurrent implementations, one implementing load balancing, the other one not. And that's it.
So, like I said, our project is about maze generation. The problem we wanted to address is figuring out if maze generation can be implemented efficiently using concurrency in Java. So, during this course, we have learned different tools and concepts about race conditions and concurrent objects and mutual exclusion. We wanted to test those theories, and we were comparing the speed of concurrency, generating the maze with different algorithms. They're using 3 different algorithms. We're using randomized DFS, randomized prim, and Aldous-Broder. We'll be testing each algorithm both concurrently and single-threadedly, and then comparing the results with graphs of different sizes. The goals of the motivations of our project were to gain knowledge on concurrency even more and thread manipulation. We wanted to talk about which algorithms are best to implement to achieve the fastest time and generating mazes. And we were curious about trade-offs between using multiple cores for maze generation or single cores, and if the benefit outweighed the cost. And we just wanted to learn more about graph theory and how it can be affected due to different algorithm and sizes.
Overall, our main goal in this project was to explore which maze generation algorithms could see an efficiency improvement if implemented using multi-threading. The different algorithms we explored were Aldous-Broder, randomized depth search, and randomized prims. The prims algorithm we use is a maze generation algorithm as opposed to prim's maze solving algorithm. We wanted to compare the different algorithms across the 2 approaches at different maze sizes to see if concurrency made a difference past a certain maze size. Comparing these sequential versus concurrent implementations will allow us to weigh the pros and cons of each algorithm and gain a better understanding of maze generation. Challenges for this project included finding the best optimized version for each concurrent algorithm. Oftentimes, threads would compete for the same cell despite our best attempts. Therefore, we had to brainstorm how each algorithm could be designed in a concurrent way and still be functional. Another challenge included threads ending before the maze had finished generating. Once those problems and other smaller race conditions were solved, our main challenges became LaTeX styling and formatting. Mazes have been found in society for millennia, in games, challenges, and stories. So what is a maze exactly? A maze is a network of paths and hedges designed as a puzzle. Mazes have the specific goal of getting from a starting position and navigating through passages and dead ends until reaching the ending destination. Mazes can be useful in a variety of disciplines today, from robotics to navigation, optimizing city planning to gaming. Mazes have their wide array of applications in our modern world. So how do we go about this? To achieve this, we are producing uniform spanning trees, that is, spanning trees that have an equal chance of occurring out of all possible combinations of spanning trees. Additionally, it was an important requirement that any arbitrary point in our maze could be reached from any other arbitrary point. So let's take a look at how the first of our maze generation algorithms worked.
This is the Alias-Broder algorithm. It's a very simple implementation of a maze generation algorithm. It implements a series of random walks until we visited every single cell in the grid. We'll go over the implementation in the next slide. However, of note, this is a very slow and inconsistent algorithm due to its random nature, and it has a lot of problems in terms of efficiency. So this is the simple idea of AldiusBroder. First, it'll pick a random spot to start on the maze. Let's say the bottom left. And it can move in the 4 cardinal directions, either up, down, left, or right. Here it can only move up and right. So it'll choose a random direction to go in. Let's say it goes up. So now it chooses to go up. It'll clear a path. It'll clear this cell's northern border and this cell's southern border so that both cells have a path to each other, as we can see here. Now, of note, this thread can move to an already visited cell, and this is where the efficiency problems occur. So now, if we go in our ideal AldiusBroder, we go right, we go up, we go left, we go down, right, we go down again, and we go right to complete our maze. And I just want to note again, this was the most ideal AldiusBroder algorithm. That head could revisit old cells it's already visited and jump across borders it's already created. And we can see that here in this example, we can see that it's just randomly moving across this maze. And and I want to demonstrate here one of the big problems of this algorithm. Although it's doing really well in clearing out all of the initial cells, we can see as we get deeper into the program, it can't find these last few cells. There's almost 30 seconds left in this video, as in 1/3 of the video left, and there's only 7 cells left. And by the time we get halfway through, it still can't find those top few cells. And that displays a big problem with this algorithm. When there are not that many cells left, it has trouble finding those last few cells until it eventually finds it. And that contributes to both the inconsistency and long runtime of this program. It just can't find those last few cells. And here we have some sequential data for the AldiusBroder algorithm. This was aggregated data from 300 runs run across multiple maze sizes, including 10 by 10s, 50 by 50s, 100 by 100s, etc. And these are all measured in milliseconds. As you can see, there's a significant drop-off in performance as we get into larger maze sizes, meaning this has a really bad time complexity, although an exact one is really difficult to predict due to the random nature of the program. Furthermore, the standard deviation here shows that this algorithm is quite inconsistent, as it strays away from singular numbers. However, we'll compare this data to the concurrent data coming up. This is the first concurrent implementation of AldiusBroder. It's a non-load balancing approach that simply throws all the threads into the grid. One consideration needs to be made in order for this algorithm to run, and we'll go over that in a second here. However, the goal of this program is for all the threads to see that there are no more unvisited cells left, and that's implemented with an atomic integer. No contention needs to be accounted for in this algorithm. If 2 threads see an unvisited cell and go for it at the same time, the end result will always be the same. And no matter who gets to set their value first, the end result will be the same. So the one consideration that does need to be made, however, is that each and every cell or thread needs to start at the same random point. If they don't, multiple independent spanning trees can be made rather than one big one. We can see an example of that here with 2 threads on a 3x3 grid starting at different starting positions. We can see they move down, up, left, right. And now this is technically completed in the eyes of both of these threads. There are no more unvisited cells left, and they can leave the program. However, what they're leaving are, instead of one big spanning tree, it's 2 independent ones. We can no longer arbitrarily travel from one point to another point. It's impossible in this maze. So in order to prevent this, each and every thread has to start at the same point. Then we can at least guarantee that there's one common point between each and every thread. Now, here's some problems with this algorithm. It doesn't really acknowledge the main issue of the sequential version. There's still points in which each and every thread can't really find the last few cells. Although the chances are increased, it's still difficult to find them all. By the time you can reap the benefits of a massive search area, like let's say with 20 threads, 50 threads, 100 threads, etc., all those threads slow down the program massively due to the fact that each and every thread is doing constant calculation, constant movement, and constant random number production. It takes a load on the CPU and thus increases the latency of this program. Furthermore, you can't really guarantee that each and every thread is doing an equal amount of work, and it wastes that increased help by just having it so that 4 threads could lollygag in the corner while 1 thread could be doing 90% of the work. We can't guarantee that each and every thread will do equal amount of work. And so we can see an example of this implementation here where they start out well, they each find the initial cells very quickly, and however, let's skip to like a minute in. We can see that now there are like 6 cells left. Now each of these 5 have to find these remaining 6. However, there's 2 minutes left in the video. We're only one third of the way through. They couldn't find those last 2 cells for over 2/3 of this algorithm running. So if we skip, we can see a minute in, they still couldn't find it. A minute in, or 30 seconds in, they still couldn't find it. Another 20 seconds in, they still couldn't find it. It takes a long time due to the fact that these cells can't find the last few cells. And now, so that's the big flaw of this program. It doesn't really acknowledge the main problem of the sequential version. So this is the data of the concurrent implementation compared to the sequential version. As you can see with 2 threads, there's a massive performance boost over the sequential version. And after 2 threads, there's a big performance drop-off. And in this slide, we can see that only 2 threads with this implementation performs better than the sequential version. Everything else either sees a massive drop-off or is slightly worse. And the reason why this 1 thread is worse than the sequential version, even though they're both technically sequential, is it takes time for the algorithm to set up threads, and therefore it sees a slight performance drop over the sequential version. This is the second implementation of Alias Broder. This is a load balancing approach. This method ensures that each and every thread has an equal amount of work to do. By splitting the grid into subsections, each thread will then take their own subsection and create an independent spanning tree in those subsections. Once each thread has finished creating their own spanning trees, they'll combine all the spanning trees at the end by erasing cells on their borders. And this is configurable by a threshold. Basically, at each and every cell on the border, there's a % chance, configurable in the program, that it'll be erased. This is by far the best approach for Alias Broder. The threads are traversing on smaller graphs, making it that you're running many Alias Broders at the same time, and it overall makes the algorithm a little more consistent. However, some problems with this, it's not a true uniform spanning tree. While it is a spanning tree, it's not a uniform one. Due to the configurable nature of this program with the threshold value on the borders, there are some configurations that are more likely than others, meaning every single spanning tree doesn't have an equal chance of forming. Furthermore, each thread has to wait for the last guy to finish. This basically means that the whole algorithm is only as lucky as its most unlucky thread. However, this unlucky thread is being run on a smaller grid rather than being unlucky on a larger grid. So here's an example of that in action. So if we move, we can see that each and every thread has their own subsection to clear. And if we skip a little bit into the video, we can see one of the threads stop. This guy stopped. He's finished with his work. However, he has to wait for his buddies to finish here. And we can see that this subgrid here will get very unlucky. And that holds back these guys who has to wait for this last guy to finish up. Now if we keep going, yada yada yada, we'll see how these threads clear the borders, and we can see now that the borders have been cleared. This is a data comparison between the second implementation, the first implementation, and the sequential version. We can see that 2, 3, and 4 has a massive improvement over the sequential version. And overall, this, the second implementation is better than the first implementation as the maze size grows. So at 500 by 500, even 2 threads for the second implementation performs much better than the first one. And the standard deviation here, which once again is a measure of how consistent the program was, is much better in the second implementation here, where it doesn't even reach 200 with 500 threads. It's even better than the sequential version, meaning that this algorithm is far more consistent. And that could be attributed to the fact that it's only as lucky or unlucky as its most unlucky thread. So now if we move, this is a direct comparison of implementation 2 to the sequential version, highlighted in red here. We can see that each and every thread count except 5 performs better than the sequential version. And after 2 threads, there is no significant drop-off. Although there is a drop-off, it's not significant. Going back, there's one optimization we could make to this implementation. When a thread finishes, instead of waiting, it could go to its neighbor's subgrid and help them out in clearing the subgrid. That's one optimization I would make for that implementation in particular. But this is basically a direct comparison of how much each implementation improved over the sequential version. And we're only going to be focusing on 2 threads here, which is represented in orange here and in blue here. We can see that as we get into larger maze sizes, the improvement over the sequential version actually decreases for implementation 1. And inversely, the improvement over implementation over the sequential version and implementation 2 is somewhat consistent. It raises the improvement over it actually increases. So that is also another point of comparison and how much better implementation 2 is than implementation 1. In conclusion, the load balancing approach saw the most improvement. It was the algorithm that was far more consistent, and it made the algorithm run moderately faster compared to the non-load balancing approach and sequential version. And overall, due to the optimized nature of this algorithm sequentially, it was much easier to optimize concurrently and produce those larger numbers in terms of improvement.
Good day, ladies and gentlemen. Today I want to talk to you about a randomized depth first search algorithm. I implemented a maze using maze generation. The basic idea of randomized DFS is to start at a random cell in the grid and visit its neighbors recursively, marking them as visited and carving walls between them. We continue to explore each neighbor recursively until we reach a dead end or visit all cells. To make the algorithm random, we shuffle the order in which we visit the neighbors of each cell, ensuring that we explore the grid in a randomized order. Continue to next slide. Okay, so this is the code implementation. I use Java. I implemented with first. We used the executor service to mark for multiple threads, and the rest was using basic Java util. We started with a grid of cells all marked as unvisited. And in each grid of cells, we choose a starting cell at random and mark it as visited. After that starting cell is there, we add that starting cell to a stack, and it signals it to be explored. While there are cells in the stack, we pop the top cell for the stack, but if the cell has any unvisited neighbors, we randomly choose an unvisited neighbor and remove the wall between its current cell and chosen neighbor. Then we mark the chosen neighbor as visited and add it to the stack. Otherwise, we backtrack to the previous cell in the stack. When the stack is empty, the maze is complete. In concurrent randomized DFS code implementation, I'll go back for a second. In concurrent randomized DFS code implementation, we, instead of doing it with one thread only and looking at only one starting cell at random, we have multiple starting cells at random depending on how many threads there are in the stack, or depending on how many threads we are implementing. Some problems and things that we consider when trying to optimize concurrency was the fact that many of the threads were getting stuck at dead ends, which kind of stalled the program and the overhead cost multiplied extensively. This made the concurrent version much slower than the parallel version. But a solution to that was an exception. We shut down the executor every time that there was and we had the thread await termination every time it got stuck in a dead end. This allowed the concurrent to be equal, or roughly equal, to the sequential version of the program. Without this small line of code, small 4 lines of code, the concurrent version performed much worse than the sequential version. Move to the next slide. Also, can you go back for a second? Also, the right side is the Java Swing implemented like picture that generated from the maze generation program. To the next slide. Like I said, the sequential and the parallel version was roughly equal. You can look at the data here. I tested it in different maze sizes. Each maze size is squared, so 25 by 25, 50 by 50, 100 by 100, and a whopping 500 by 500. This you can see that the means are roughly equal in each section. The only difference was in the last 500, which again ran into some problems trying to generate it because it's a recursive program. The problem with recursive programming is that the recursive programming relies on a stack, and when there is stack overflow, it shuts down and cannot handle big map sizes. So in turn, we had to use a command line prompt to give space when running the program. Well, I ran it with 10 megabytes to get the 100 stack to work. In future programming things, although recursively is the most normalized version of randomized DFS, an iterative method should be considered. And as you can see, the standard deviation did not differ very much. The only difference was in maze size 100 by 100. The sequential, for some reason, had a lower standard deviation than the other threads or other concurrent versions. But when you go to 500 by 100, then the standard deviation is about the same as well. So there isn't that much difference. Next slide. Here are some charts. As you can see, at 500 by 500, there was some difference. But in general, it's about equal throughout the board, across the board. And the next slide. Yeah, some considerations for future testing would be a different testing environment, probably a better computer, to be honest, and a more standardized testing environment where things are equal at all times, without anything background running, without any background processes that are affecting the times. And that would help get more clear results. Also, I have to mention this because I forgot, is we tested with 100 runs for each size and each thread count. We could raise that number by any means. We could raise it to 500 to 1,000 runs and have even more clear results. Another thing we could do is different programming language. Java is not the best for concurrent implementation. It's not the fastest. And as there was some difference at 500 by 500, it could be possible that with a faster and easier, more efficient language that implements multiple threads better, that there could be more of differences. Another thing was the iterative approach. Like I said, recursive, since the randomized DFS is normally recursive, there was some stack problems, and we had to manually give space when running the program for higher maze sizes. Those are my considerations, and those are the end result of randomized DFS.
So in the traditional PRIMS algorithm, the way it works is that a node in the graph will be selected, and then it will look at the all of its adjacent nodes and find the one with the smallest edge weight. So the key difference between this and randomized PRIMS algorithm is that the grid is unweighted, and instead what the algorithm will do is it'll select the cell at random as long as it's a part of the frontier of the maze. So there's a few steps for randomized PRIMS algorithm. Right, we start with a grid that's empty, and we choose a random cell in the grid, and then that will be marked as being inside the maze. And the second step is to mark the cells next to that cell as frontier cells and add them to a list. And step 3 is to choose a random frontier cell from the list and carve a passage from that frontier cell into an adjacent cell. And if it's adjacent to 2 cells that are already in the maze, then one will be picked at random. And then you repeat steps 2 and 3 until there are no more frontier cells in the maze. At that point, the maze has been finished. So for the concurrent implementation of this algorithm, a few points to be made is first that the main loop is inherently sequential, so that cannot be done in parallel. So our method for the concurrent implementation was to run the mark function instead. So when the mark function is called, all of the frontier cells that are added to the list will be added by different threads. And we tried this approach using 2 threads and 4 threads. So I have some graphs here for the sequential version. You can see from these graphs that randomized prims algorithm is a very fast algorithm. On the low ends with a grid of about size 50, it takes maybe a few milliseconds on average. And then on the high end with the largest grid size that I tested it on, which is 1,000, it was about 120 milliseconds on average. And the standard deviation was also very good. With grid size of 50, it was about maybe 2 milliseconds. And then the standard deviation at grid size of 1,000 was about 12. Now for the first parallel implementation, which used 2 threads, you can see immediately that it's much slower than the sequential version. So at first, it's roughly the same. It's roughly the same mean at the smaller grid size, but then as it increases, you can see once it gets to 1,000, a grid size of 1,000, it's a little over 400 milliseconds, which is much slower than the sequential version. And then when you look at the standard deviation, it's also worse. It starts off at about 2 milliseconds at about a grid size of 50, which is about the same as the sequential version. But by the time the grid size reaches 1,000, the standard deviation is about 25 milliseconds. And then the version of this with this algorithm with 4 threads was even slower than the previous one. So you can see at a grid size about 50, it was around maybe 10 milliseconds. And then once it hit 1,000, it was approaching, once it hit a grid size of 1,000, it was approaching 600 milliseconds. And then the standard deviation is much worse as well. Right, at a grid size of 50, it's around 3 to 4. And then by the time it hits a grid size of 1,000, it's at maybe 26, 27 milliseconds. So these 2 graphs here, these have all of the versions that I tested kind of all displayed next to each other. And you can see clearly on the first graph that the sequential version is significantly faster than the concurrent versions. Right, the first one with 2 threads is almost 4 times slower, and then the third one is around maybe 4.5 times slower. Then you can see on the graph to the right, which show the line graph, that the speed gradually increases the mean runtime gradually increases for the sequential version, but the parallel ones have a much steeper increase.
Overall, the algorithms that were already optimized in the sequential implementation saw no significant improvement in the concurrent approach. This include depth-first search and prims. In contrast, the algorithm that was not optimized in a sequential approach and was initially slow saw a saw a greater improvement in the concurrent implementation, although the concurrent implementation was still much slower than both DFS and PRIMS.